I'd like for this video to serve as a consolidation of several things that I've learned regarding 3.4 and 3.5. So this is the homework from homework number 5, and I'm going to solve the problems and try my best to explain how they're done, or really just the way that I do them at least. But for number 9, it essentially wants us to find the derivative of the function. So the function is given, it's under root 5x plus 1, and it wants us to find its derivative. So essentially, when we're looking at this function, it looks unfamiliar, right? It looks as if though we haven't done something like this before. But the idea is when you have square roots in the context of derivatives, what you want to do is you want to express this function or this type of function as something that we are familiar with. And what we're going to say is that f of x, so I'm not actually taking the derivative yet, so I'm not going to put that comma, as it were. I'm just expressing this function as something else that is equivalent to it. So in this case, what I can say is that this is 5x plus 1 raised to the 1/2. Now, why do I say this? Well, this goes back to a basic exponent property. The idea is that if you have, so this is the idea, or really the background behind why I say this is true. If you have x2, or let's say if you have x, you have under root x, the idea is that there is an implicit 2 here on the index if the index is not specified. So if I say it's 3, then it's the cube root. But if I don't put anything there, then that means that there is an implicit 2. And by implicit, I mean that it is implied. And if I don't raise x to anything, that means that there is an implied 1. So this is the true form if you were to sort of pull the curtain behind what it means to do under root x. Well, this is the true form of under root x. There's an index of 2 and there's an exponent of 1 here. Now, I could, of course, change the index and the exponent. I could say x to the second, and the property would still remain the same. This is the index and this is the exponent. But the idea here, or really you could think of it in a formulaic way, is that x to the a to the n, right? So if my index is a and my exponent is n, the idea here is that this becomes x, and then we have n over a. So the index goes to the denominator, and the n actually goes to the numerator. So this is what one would call a fractional exponent, because it's an exponent, but it's also a fraction. So if I had anything, right, if I had x to the 3/4, I could express this as a square root. I can put the 4 here, and I could put the x, of course, underneath, and I could put the 3 here. And then I'll say that this is this would look like this then. And I could go the other way around as well, right? I could say this, well, okay, well, this is just x to the 3/4. So that's the basic idea. So I can then, so in this case, in this analogy, instead of having x, I just have 5x plus 1, and that would be so in this case, since it's not specifying anything, that means there's an index of 2, and since the inside is not raised to an exponent that's explicitly defined to us, we can then say that this is actually raised to the first power. So you can think of this as if though it were x, right? What would you have done if the inside was x? Well, you would have said that this is just x to the 1/2, correct? Because you're taking your 1 and you're putting it in the numerator, and you're taking your 2 and you're putting it in the denominator. But the problem is that it's not x, right? It's not x. It's actually 5x plus 1. So you're saying that this is actually 5x plus 1 to the 1/2. So in the place of x, you actually have 5x plus 1. And everything else that we discussed, the dynamics of the rules of changing from a radical to a fractional exponent, all of that is consistent. So just for an example, if I had 4x plus 2, right, and if I had a 3 here, and let's say I had a 2 here, well, this would come out to being, well, you'd have 4x plus 2, and then you're raising it to a fractional exponent, so that 2 goes in the numerator, the exponent goes in the numerator, and the index goes in the denominator. So that would essentially be your equivalent form. So why I haven't written this as the derivative is because I actually haven't used any derivative rules yet. I've simply expressed 5x plus under root 5x plus 1, which is a function, as something else that it's equivalent to. And why I've done that, right? It seems kind of random. Sure, you can do that because we've proved we can do that. But why should we do that? Well, we should do that because now what we can do is we can apply two things. We can apply the power rule. We can apply the power rule, and we can also apply the chain rule. So the power rule, and this puts us, being in this position puts us in a position where we can now apply the power rule and the chain rule. Now, let's first talk about the power rule. And again, you don't have to think about this as 5x plus 1. You could instead think about it as being a simple big X, right? If it were a big X, what would you have done? Well, you would have brought if you were to use the power rule, that is, you would have brought the 1/2 down. You would have said this is equivalent to 1/2 and then 5x plus 1. And then what you're doing is you're subtracting, you're doing 1/2 minus 1 because you want to decrement the exponent. Remember that x to the n is actually nx n minus 1. You bring the exponent down and then you decrement the exponent. And so we've gotten there, right? We've brought in the exponent down, but we actually haven't decremented the exponent. So if you do 1 minus 2 or 1 over 2 minus 1, if you do 1 over 2 minus 1, which is the same thing as saying 2 over 2, you're going to have negative 1 over 2. So this exponent here actually becomes negative 1 over 2. But this isn't where the problem ends. If it were that simple, then we wouldn't have to apply the chain rule. And remember that we're sort of, this is taking this one step further, we'll be using the chain rule. But as of now, we treat the inside as if though it were x, correct? So we brought the exponent down, we kept the inside the same, and then we decremented the power by 1. And now what we essentially want to do is we want to multiply by the derivative of this, of the inside function. We want to multiply by the derivative of the inside function. So what we're going to say here is we're going to say times the derivative of 5x plus 1. So we're not taking the derivative of 5x plus 1 and putting it in these parentheses. No, this is part of our answer, right? We're just multiplying this by the derivative of 5x plus 1. So the derivative of this, we took the derivative of that, and now we're taking the derivative, we're multiplying by the derivative of the inside function. So what would that look like? Well, we're going to have everything that we had before, 5x plus 1 to the negative 1/2, and then we're going to multiply by the derivative of this. Well, what is the derivative of 5x plus 1? Well, it's just 5. Because you can think of this as two functions being added. So you take the derivative of each term individually, each function individually. So what's the derivative of 5x? Well, it's just 5. What's the derivative of 1? Well, it's 0. So you're left with 5. And then what you can do in this stage is you can multiply, things that you can multiply. Note you can't distribute, right? But you can multiply your term. So you can say this is 5 over 2 times 5x plus 1 to the negative 1/2. Now, this comes back to another rule of exponents, that if you have x to the negative 1/2, well, this is the same thing as 1 over x to the 1/2. So once you bring it to the denominator, implicitly there's a 1 here. When you bring that to the denominator, you actually have to flip the sign. And the same can be said if it were 1 over x to the 1/2. Well, when you bring it to the numerator, you want to flip the sign. You want to make it negative, right? So same idea here. We take 5 and then we have 2 in the denominator, but we want to take this portion into the denominator, but we got to flip the sign in order for that to work. So we're going to say 5x plus 1 to the 1/2, right? Because we made it positive. And remember that x to the 1/2 is actually just under root x, right? The 2 goes here, the 1 goes here. None of them are mentioned usually, but that is the equivalent form. So 5x plus 1 under root 2, if this were x, what would you have expressed this as? Well, it would be 2 times, the 2 would go here, and then the 5x plus 1 would go inside. And then that's just to the first power, which we don't really specify. So we're just going to say that this is 5 divided by 2 times the under root 5x plus 1. And then that's essentially your answer. So this is your so this is f prime, right? This is f prime. This is f prime. This is the original function. And we had to use a couple properties of exponents to get it into a form where we can use the power rule. But using the power rule wasn't enough, simply because, you know, we had something inside the inner function, so we had to multiply by the derivative of the inside. And that's how this problem works. This next problem is slightly tricky, but essentially we want to use or leverage our differentiation rules in order to be able to solve something like this. But the basic idea here is that you want to think of e to the x as a function, right? And you want to think of sine of x as a function. So when I multiply e to the x and sine of x together, I'm essentially multiplying two functions. And we know that the differentiation rule tells us that the derivative, if I have two functions, f of x times g of x, this is essentially equal to the derivative. It's going to be the derivative of the first function multiplied by the second function plus the derivative of the second function multiplied by the first function, right? So this is nothing but the product rule, right? This is the product rule. So in this case, my f of x is e to the x and my g of x is sine of x, correct? Now, in this case, we just have it slightly more complicated, right? I mean, you have x is not x in this case. E to the x is not e to the x, it's e to the at, correct? And it's not sine of x, it's sine of bt, right? So instead of you having an x in the numerator, not in the numerator, but as an exponent, you have at. And then instead of having x inside the parentheses of sine, you have bt. But we're going to get to that stuff, but that doesn't change the underlying fact that this is nonetheless two functions being multiplied together. So essentially what we're going to do is we are going to put these two functions in this form so that we know what we should take the derivative of, what we should multiply with, so on and so forth. So what I will say is that f prime of t, right, so it's with respect to t, is equal to, well, what we're going to do in this case is we're going to say d over dt. Now, why have I introduced dt? Well, the idea is that when we were doing f of x, we were doing, if we had f of x equals something, we did d over dx, correct? But if we have f of t, then we're differentiating with respect to t, correct? Which means that all the t's in this case are just like the x's when we were working with functions, the derivative of functions before. So remember how we said, okay, what's the derivative with respect to x of x? Well, we said that was 1. Well, if I say what's the derivative of with respect to t of t, well, that would also be 1. So that means that if I take the derivative of these t's here, those should be 1. And then the a and the b, so this is the a, this is the b, these are constants. These are constants. So a is like 2 or 3 or 4, and b is also 2, 3, 4. It's not a variable, right? We treat a and b as if though they were constants. So, and t is a variable. Just as I had 2 times x, where x was the variable, 2 was the constant. Over here, we treat a as the constant and t as the variable. So if I asked you what's the derivative of, with respect to t, of course, what is the derivative of a times t? Well, a is a constant, so we can pull that out, right? We can say that's just a times the derivative of t. Well, what's t? It's a variable, right? Just as x was a variable. The derivative of a variable like x or t or y, well, not y, but the derivative of x was 1, so the derivative of t must also be 1, which means the derivative of a times t is just, in fact, a, because it's a times 1, which is just a. So we want to keep that in mind, as we're working through this problem here, because you look at a, you look at b, you look at t, and you're not too sure what to think. But a and b are constants; they are fixed. But t is a variable, so t is going to play the role of x in this case. So we're taking the derivative. So we're trying to put these two functions being multiplied together. We're going to put it in this form, and that's going to tell us what we should multiply with and what we should take the derivative of. So this is e and then a to the t, right? And then we're going to multiply with the second function, right? So we're taking the derivative of the first, multiplying by the second, g of x. So this is our g of x, right? This is our g of x. This is our f of x. Right? So we took the derivative of f of x. We put it in, we didn't actually take the derivative. We put it in a box that's going to tell us later on to actually take the derivative. And then we multiplied by sine of bt, not sine of x. It's a little more complicated this time around. It's sine of bt. And then we add to the derivative, so d over dx of, well, now we're taking the derivative of g of x, right? So we're going to take g of x. This is our g of x here. We're going to take it and we're going to put it inside this box so that later on we know to take the derivative of sine of bt. So we're going to say sine of bt. And then, of course, multiplied by f of x, and we know our f of x is a to the t, right? E to the a t. So it's multiplied by e to the at. And I think what I'll do at this stage is I'll actually put like a curly brace here so that we know what we're taking the derivative of, right? And we know what we're multiplying. So at this stage, you can look at these problems individually. You can go off to the side and find the derivative of e to the at. You can find the derivative of, well, the sine of bt, so on and so forth. And then you can come back and then just merge all of this together and do the algebra if so your problem warrants algebra. But, first looking at this off to the side, right? We're going to look at what is the derivative of e to the at, right? What is that? Well, we know that we know that the derivative d over dx of e to the x, well, what's that? Well, that's just e to the x. So if I make my at, if I make my x, in this case at, then my derivative should also follow. So the derivative of anything is e to that anything. So the derivative of at is e to at. But the problem here is that I have an inner function. It's not just x. If it were just x, I'd leave it at that. But it's not just x. It's at. That means I need to multiply by the derivative of that inner function. If it were just x, I would have left it. I would have left it at that. I would have just said it's e to the x, and I would have let it go. But the problem is that it's an inner function, right? There's a function inside, which is at. So I'm going to take the derivative. I'm going to take the derivative of at, right? So this is going to stay in my problem. I'm just going to multiply this part. This is going to stay in my solution, rather. This part is going to stay in my solution. But I'm just going to multiply by the derivative of the inner function. And then I'm going to represent that as sort of an answer. So what I would say in this case is I would say this is just e to the at. That's going to stay times the derivative of at. Well, we said before that a was a constant. So we can pull the constant out and multiply by the derivative of t. So we're pulling the constant out and we're multiplying by the derivative of t. Well, what is the derivative of t? It's 1, right? Just like the derivative of x was 1, the derivative of t is 1. So we're going to multiply a times 1. Well, that's just a. Which means I can now go back. I can now go back here before I digress. I can go back here and I can say that the derivative of e to the at is in fact just a e to the at, right? Or e to the at times a, right? Doesn't really make a difference. And we're going to multiply by this. So we're just going to multiply by sine of bt, correct? And then we're going to do the same thing here, except now we're finding the derivative of sine of bt and multiplying by e to the at. So what we're going to do now is we're going to pretty much do the same thing, right? We can go off to the side and find the derivative of sine to the bt. So we know that the derivative of sine of x is actually just cosine of x, correct? So if I say, what's the derivative of sine of bt? Well, that's just going to be cosine, but my x was not x in this case. My x was bt, right? You can see that comparison, right? So if I change my x in here, I have to change my x here. So it's not going to be sine of the derivative of sine of bt is the cosine of bt, correct? So it could, like if I had, if I had the sine of a red dot, well, the sine of a red dot is cosine of a red dot. Okay, the same thing here, sine of bt is cosine of bt. But the problem is, and this is where we take it one step further, the problem is that that inside, it's an inner function, right? If it's not x, then consider it an inner function, or if it's not t in this case. But so we multiply by the derivative with respect to t, of course, and this should be respect to t. This should be respect to t. All these x's should be respect to t. Just a note there, I sort of messed that up, but hopefully you understand that we're differentiating with respect to t, not with respect to x. But we multiply by the derivative of bt. So you ask yourself, well, what's the derivative of bt? Well, I said before we began that b and a are constants. So you can pull the constant out. This is still in your answer, by the way. But you pull that constant out and then you multiply by the derivative of t. What is the derivative of t? The derivative of t is 1, just like the derivative of x is 1. So your answer is, so it's 1 times b, that's cosine bt times b. So what we did was we said the derivative of sine of bt is cosine of bt, right? Just like the derivative of anything is cosine, well, the derivative of sine of anything is cosine of that anything, times the derivative of the inside of that anything. And we know that the derivative of b times t is just b, because the derivative of t is 1, so b times 1 is just b. So that's the idea. So that's our answer. That's our takeaway, and we're gonna put that back before we began this slight digression here, and we're gonna say that the derivative of sine of bt. So we're gonna say sine of bt is cosine of bt times b, or you could say b cosine of bt, right? And then of course we multiply by e to the at, right? So what this structure does for us is it tells us what to take the derivative of, what to keep the same, what to take the derivative of, and then what to keep the same. And that essentially concludes your answer. But if you want to be a little more peculiar, like if you want to be a little more particular about it, you could factor out an e to the at, and then what that would do is it would leave you with an a, right? You're not including your e to the at, because e to the at divided by e to the at is 1, and a times 1 is 1. So then we have times sine of bt, correct? These are being multiplied. And then we add that to, so we're going to scrap the e to the at here, because we're sort of factoring out the e to the at. So that's just b cosine of bt. And that is essentially your answer. So the takeaway here is that e to the anything is e to that anything. So if I say e to the 2x, well, that's e to the 2x, right? But the thing is, you have an inner function here. If it's not x, if it's something else, if it's 2x, 3x, anything else that's more complicated, then take the derivative of that. So we multiply by the derivative of 2x. So that's just e to the 2x, right? Keep that in your answer, multiplied by 2, because the derivative of 2x is 2. So that's 2e to the 2x, right? So that's the basic approach. But in this case, it wasn't anything. It was bt, where b was a constant, t was a variable. So we can always pull that constant out and then multiply by the derivative of t. What's the derivative of t? It's 1. So b times 1 rather, is just b. So we applied that kind of reasoning quite a bit here, but we got to the right answer, right? And we wanted to understand that, two functions are being multiplied, so we got to use the product rule. And then we can just go back and evaluate these individually, and then come back and then join them all together, and then factor if need be. So this problem here is certainly tricky, right? Because what it wants you to do is it wants you to use the chain rule twice. And sort of as a preface to actually doing this question, let's look at a question very similar to it, but not as complicated, so that we can come back and revisit this and try to get some intuition for this particular question. But if I said, what is actually, let's look at this, correct? Let's go off to the side and let's just look at sine of e to the 2x. Let's not think about anything else. Think about this as if though it were a different question, correct? So if I randomly came up to you on the street someday and I said, what is sine of e to the 2x, right? Or actually, what is sine? Yeah, right. So what is sine of e to the 2x? Well, what you would say here is you'd say, okay, well, I have an outside function, which is sine to the x, right? And then I have an inside function, which is e to the x. So this is actually sine to the x, right? And e to the x. But instead of it being x in this case, so instead of the inside being x, it is instead e to the 2x, correct? So we know that the derivative of sine of x is cosine of x, correct? So if I just changed that x to e to the 2x, well, I should also change it in its derivative. So if I said that this point inside here is e to the 2x, then it must also be the same here. It must be cosine of e to the 2x, correct? So that means that if I wanted to take the derivative of this, I would say that the derivative of this is equal to cosine of e to the 2x, right? E to the 2x. And I kept that inside the same, right? So in this case, it was sine of x. And we know that the derivative of sine of x is cosine of x. But if I change that x to anything, then it must also correspondingly follow to being the x of that anything when we pop out the derivative. So that's what we did here. We know that it's cosine of x, but instead of it being x inside, it's e to the 2x. So we changed that inside to being e to the 2x. But again, that there comes a problem that the inside is not x. It's something more complicated. It's an inner function. So what we do is we multiply by the derivative d over dx of e to the 2x, of that inside part, correct? So this stays in our answer. This is in our answer. But the issue here is that we want to multiply our answer by the derivative of the inside, which is e to the 2x, and we're going to keep the rest the same. So we're going to write cosine of e to the 2x here, but we're going to multiply by the derivative of the inside. So what exactly is the derivative of the inside? Well, the derivative of the inside, if I asked you what's the derivative of x, correct? You would say, well, that's just e to the x. But if I changed the x to being 2x, it has to follow. It has to follow. That means the derivative of e to the 2x is e to the 2x, just like the derivative of e to the 3x is e to the 3x, correct? But we're missing a step. We're missing a step when we say this, because when we take the derivative, when we say that, okay, the x's match and whatnot, this is still an inner function. It's not x. It's not x. It's something more complicated. So you have to take the derivative of the inner function. So you're multiplying by the derivative of 2x, which we know comes about to being 2. So this is e to the 2x times 2, correct? So same thing here. We know that the derivative of e to the x is just e to the x, but in this case, the x in this case is 2x. So we're going to say that the derivative of e to the 2x is e to the 2x, right? Just like we changed the 2x's here and they followed, right? So e to the 2x is the derivative of e to the 2x is e to the 2x, but we want to multiply, right? We want to multiply by the derivative of this inside guy. So we're multiplying by the derivative of 2x, right? Everything stays the same. We're following it down. The derivative of e to the 2x, or 2x rather, is 2. So that's just e to the 2x times 2, correct? So this is essentially your answer for the derivative of sine of e to the 2x. And just to recap, we said sine of e to the 2x, we said sine of e to the 2x. So we took the derivative, we said that the derivative of sine, the outer function, is cosine of x. But in this case, my x is something more complicated. So it's cosine of e to the 2x, not cosine of x. And then we said, wait a second. Now we're looking at the inner layer. So it's the outer layer is cosine of x, which is cosine of e to the 2x. So then we multiply by the derivative of the inside, which is the derivative of e to the 2x. And then this is like a separate question almost, right? We keep what we had the same, which is e to the 2x. We multiply by the derivative of this. The derivative of e to the x is e to the x. But if I changed it to 2x, it would be the e to the 2x. So the derivative of e to the 2x is in fact e to the 2x. But then I want to multiply by the derivative of the inside. That's just 2. Right? Because the derivative of 2x is 2. So my final is 2 cosine of e to the 2x times e to the 2x, or right. So 2 times cosine of e to the 2x times e to the 2x, which is essentially what we got before. So that's how we handle 3-step chain rules, right? Before, what we were doing is we were looking at stuff like this, sine of 2x, right? So what we did here was, we just said that this was cosine of 2x multiplied by the derivative of the inside, which is just 2. And then that was our answer. But what if what is inside this bracket needs a chain rule as well, right? E to the 2x needs a chain rule, right? So when we do the derivative of the outer, which is cosine of e to the 2x, and then we multiply by the derivative of the inside, well, the inside is in itself another chain rule, right? So when we take the derivative of this, it's e to the 2x, but times that inner function, which is times the derivative of 2x, which is 2. So that's how we got this far, right? So now that we know how to handle stuff like this, we're going to now revisit the problem. We're going to revisit the problem, and we are going to say, well, okay, we know that this is of the form e to the x. This is of the form sine of x, correct? The exception is that the x is something different, right? The x in this case for e to the x is this guy. And the x that's supposed to be inside this bracket is e to the 2x. So the idea is that when we're doing two functions multiplied together, these are two functions, well, not multiplied, but added together, what we can do is we can take the derivative of the individual functions. So we can say e to the sine of 2x plus the derivative, and I'm not actually taking the derivative yet. What I'm doing here is I'm just writing what we're going to take the derivative of, right? So if you remember the rule that the derivative of two functions added is actually just the derivative of them both added, right? So you take the derivative of this guy and then the derivative of this guy, and then you just add them together, and that is your final outcome as being a derivative. So what we're going to do is we're going to go off to the side and we're going to find the derivative of e to the sine of 2x, and then we're going to do the same. We actually already did the same thing. So this comes down to just taking the derivative of this and then just adding it to the derivative of this. So this is, what is the derivative of e to the sine of 2x? Well, we take the derivative here, e to the sine of 2x. And what we're going to do is we're going to say, okay, well, this is well, what is the derivative of e to the x? Well, it's e to the x. But if I change that x to sine of 2x, that should follow. So the derivative of e to the sine of 2x, just as though e to the x was e to the x, the derivative here is e to the sine of 2x, right? So it's e to the sine of 2x, not e to the x. It's not that simple anymore. We know that the derivative of e to the x is e to the x, but the derivative of sine of 2x is the e to the sine of 2x. But then we want to multiply. We want to multiply by the derivative of the inside. So sine of 2x. We're now multiplying by the derivative of the inside. So we keep this the same, but we're multiplying by the derivative of the inside of e. And if you do this, so this stays the same, e to the sine of 2x. And then we multiply by this guy. So the outer layer first, which is cosine of 2x, right? And then we tackle the inner layer. So now we're going to say the derivative of the inside. That's the derivative of 2x. So that means this is, which we know is just 2. This comes about to being 2. So this is e to the sine of 2x times cosine of 2x times 2, which means this is 2, right? E to the sine of 2x times cosine of 2x. This is our derivative for this guy. And if you remember, this is our derivative for this guy. So the idea is you go off to the side, and essentially what you're doing is you're finding their derivatives individually, and you're then pairing them back up together. So if we pair this up, right, and if we pair this up, we're going to get e to the, so we're going to get 2e sine of 2x times cosine of 2x, right, added to this guy, the derivative of this guy, right, which is the cosine of e to the 2x. Well, let's add that 2 there, right? 2 times the cosine e to the 2x times e to the 2x. That's your answer. That's your answer. Now, of course, what you could do at this stage is you could factor out, well, I don't see any need to actually. There's really no need to factor out anything. In fact, you can even if you wanted to. But this is essentially your final answer. So this was a 3-step chain rule, slightly more complicated than what we were doing before, where it was just, once you take the derivative of the inside, that's it. But in this case, it's like you're peeling an onion. You have to go layer into layer into layer until you can't do so anymore. So this question here wants you to find the derivative of sine of xy equals cosine of x plus y. And in this particular situation, we want to use implicit differentiation. And the steps are essentially very straightforward, and they seem to be consistent for multiple problem types involving implicit differentiation. And the basic idea is that you take the derivative of both sides, and then you distribute so that you have a bunch of y prime terms, and then you isolate y prime so that you can equate your equation in terms of y prime. And we'll talk more about what we essentially mean by that. So we're first going to say that we're going to take the derivative of both sides. So what we'll do is we'll say that this is the derivative. Actually, let me zoom in here. We'll say that this is the derivative, d over dx, of sine of xy equals the derivative of cosine of x plus y. Now, you could very well just sort of go off to the side and take the derivative of this, and go off to the side and take the derivative of that, and then just put them back. And maybe that's not a bad idea. So if we were just looking at the derivative of sine of xy, well, what is the derivative? What is the derivative of sine of x? Well, it's cosine of x. But in this particular case, the x is not an x, it's actually xy. So if I put xy here, then the derivative should be cosine of xy. So if I added that y, it should be cosine of xy. If I added a z, it should be cosine of xz. So sine of anything you could have inside is cosine of that anything. But if that something in between is more complicated than just x, then you have to take the derivative of it and that's the chain rule. So the sine of xy is actually just so the derivative of this is cosine of xy. But the issue here arises when we essentially want to or have to take the derivative of the inside, right? We said that. If it were just x, we would leave it alone, but if it's anything more complicated than x, then we want to take the derivative of the inside. Now, this is now again a separate problem that you can go off to the side and solve and then come back. But we'll try to keep some consistency here. Remember that cosine of xy, this is going to stay in your solution. But the basic idea is that we want to take the derivative of x times y now. Now we're going to eventually have to take the derivative of y, but there are essentially two rules you want to remember when working with implicit differentiation, is that the derivative d over dx of y is y prime. That's one possibility. The other possibility is that the derivative of y squared or y to the third or y to the fourth, the derivative of that is using the power rule, but then you just add a y prime. So if I say that, what is the derivative of y, to the fourth? Well, you just use the power rule. It's 4y to the third, but then you just want to add a y prime. So if there is nothing, if it's not raised to anything, just add a y prime. But if it is raised to something, in this case, use the power rule and then just add an extra y prime. That's how it works. So we're going to eventually have to take the derivative of y. So once you get down to doing that, remember, if it's not, if we don't have to use the power rule, just add a y prime. In this case, the derivative of y would just be y prime. But it's a little more complicated than that. And it's complicated because this is an x and a y. They're being multiplied together. This is calling for the product rule. X is a function, y is a function. So if you have two functions, being multiplied together, then the derivative of those two functions, you have to use the product rule on it. So this is still going to stay in our answer. We're still going to have cosine of xy, right? But then we're just going to multiply by the product rule of this guy. So the product rule states take the derivative of the first, multiply by the second, and add that to the derivative of y and multiply by the first, that's x, right? So what would this come out to be? Well, we're going to keep that guy that we had. We're just multiplying this by the derivative of this guy. So the derivative of x is 1. So we're going to say this comes about to being 1. But what's the derivative of y? Well, I said that if you're ever asked what the derivative of y is, just write y prime. So it's just y prime plus, well, okay, we're not supposed to take the derivative of y. We're just supposed to multiply by y. So the derivative of x is 1, and then multiplied by y is just y. So it's not y prime, it's just y. We're not taking the derivative of y. We're taking the derivative of x and then multiplying by y. Then you're asked, what's the derivative of y? Well, the derivative of y, we said, is y prime multiplied by x. So I'm just going to put the x here. I don't want to put the x here because it'll make it seem like a function, but I'm going to put the x here, same thing. So this is essentially your the basic idea, and the key thing to take away is that you're essentially what you essentially want to do is you want to ensure that when you're taking the derivative of y, it's just y prime, and then when you're taking the derivative of something more complicated like y to the fourth, that's y 4y to the third times y prime. So you just tack on another y prime. So this is the full derivative. This is the full derivative, and we could actually take this a step further by actually distributing. So it's going to be actually, do we have to distribute? Yeah, I suppose we could distribute this. We could say that this is cosine of, it's y cosine of xy, and then plus, this goes here, and then we distribute here as well. We're going to say xy prime cosine of xy. Okay, so this entire thing is essentially the derivative, right? It is the derivative of this component. So we can go back over here and then just add this component that we just found the derivative of. So we're going to add this process, or we're going to add the conclusion of this process. We're going to say that the derivative of sine of xy is y cosine of xy plus x y prime cosine of xy. And now we're asked to find, what's the derivative of this? Well, if I asked you what's the derivative, what's the derivative of cosine of x, you would say it's negative sine of x is what you'd say. But if I change that x to like a black hole, then the derivative must be minus sine of that black hole. But in this case, that black hole is x plus y. So I'm going to say the derivative here is minus sine x plus y, right? But the inside, it's more complicated than x. It's not just x, it's x plus y. So I'm going to take the derivative of the inside. So that's going to be the derivative of x plus y. What's the derivative of x? That's just 1. What's the derivative of y? It's y prime. So this is y prime. Remember, you're taking, you can think of taking the derivative of x plus y as like a separate problem, right? You're taking the derivative of x. There are two functions being added, so take their derivatives and then add them together. The derivative of x is 1. The derivative of y is y prime. So, the derivative of the inside is just, well, this is 1. The derivative of x is 1. The derivative of y is y prime. So it should be 1 plus y prime. So we're multiplying by 1 plus y prime. Does that make sense? Because the derivative of x plus y is 1 plus y prime. So we put that here, the derivative of the inside. And then at this point, you could, distribute this negative sign, perhaps, right? So what you'll say is you'll have everything that you had before. You want to keep that. You want to keep that the same, plus x y prime cosine of x y equals. So we're going to distribute to the 1, and then we're going to distribute to the y prime. So this is negative sine. It's just the same. Negative sine of x plus y. We distributed that to the 1. And now we're going to distribute that to y prime. So that's negative y prime sine of x plus y. Okay. And we'll try to move this guy somewhere to the. Okay. So that's the idea, correct? And now what you'll notice is that there are some terms that have y prime in them, right? What we want to do is we want to throw these guys off to the, left. This one is already at the left, but we want to get this guy to the left, and all the stuff that doesn't have y prime in the term, we want to get that to the other side. So what we're going to do is we're going to bring this to this side, which would mean we would have to add y prime sine of x plus y to this side. And then we're going to subtract this to get this to that side. So what that would look like, in essence, is something like, it would look something like this. So we're taking this to the other side, correct? So we're just going to have x y prime cosine of xy. We're going to have that on this side. And then we would have had this. So what we'll do is, yeah, so we're going to have this on this side. So we'll say plus y prime sine of x plus y, because it's plus now, right? It was negative on this side and now it's plus, equals what we had before on this side, which we didn't do anything with. And then we brought this to this side, right? So that's minus y cosine of xy. So now you have all your y terms on one side and all your, or rather you have all your y prime terms on one side and all of your y terms on the other side. And what you'd want to do at this stage is you'd want to factor out a y. And remember, this is not random. What we want to be able to do is we want to say, okay, y prime equals something, right? That's what we're trying to do. We're going to factor out a y and we're going to get that y alone. And then we're going to get y prime equals something. So y prime, if we factor that out, right, we're going to be left with x cosine of x plus y plus sine of x plus y equals everything we had on the left, everything, or rather the right, everything we had on the right. And then what you'd want to do is you want to divide both sides by this so that they would cancel out. And then you'd have y prime equals negative sine of x plus y minus y cosine of xy over, you divided both sides by this, so you're going to have x cosine of x plus y plus sine of x plus y. Or sorry, that should honestly just not be x plus y, it should be xy, right? Just xy. So it should be cosine, x cosine of xy, x cosine of xy, and then we'll have plus sine of x plus y, right? I'm not too sure why I added that plus there, but as you can see, it was always xy. So so sorry about my dog, but what you could do then is perhaps you could factor out a negative, right? You could then say y prime is equal to negative sine of x plus y. You're factoring out a negative, so plus y cosine of xy. A lot you could do here, right? And then say that, you have the denominator the same. But as a general answer, this would be your answer if you weren't trying to simplify this down all the way. So this question here essentially wants you to find the derivative using implicit differentiation, but it wants you to take it one step further, right? So you don't only want to find the derivative, you also want to use the slope of the tangent line, well, not the slope of the tangent line, but the equation of a tangent line to plug in values. And then from there, you're going to get the equation of the tangent line. So the equation of the tangent line, depending on which one you use, is either y equals mx plus b, or in this case, what I usually use is y minus y1 equals m, and then x minus x1. That's what I usually use. But the thing is, what you'll notice is like they've given us an x value and they've also given us a y value. So we have this, right? And we also have this, right? Because we can put our y value and our x value, but the problem is that we're missing the m, and the m is essentially the slope. So it's important to know where this comes from, right? This m is the slope of the line in question. And that slope will be found once we take the derivative of this and then plug our x value into that derivative. So we're essentially finding the derivative function. When we're finding the derivative, we're finding the derivative function. That derivative function will take in our x value and it will tell us the point, it will tell us the slope at that x value. So that's the basic idea. So first we're going to find the derivative, and then once we find the derivative, we're going to plug in the x value into that derivative, and then whatever comes out is the slope at that x value. Okay, perfect. So the first step is to take the derivative of both sides, so x squared minus xy minus y squared. So we're taking the derivative of this side, and we're also taking the derivative of this side. So again, two things to remember, that the derivative of y is just y prime. So we can, and this is a bunch of functions being added or subtracted. In this case, they're being subtracted. So what we can do is we can separate the functions individually and then take their derivatives and then subtract them at the end. So the derivative of this, then the derivative of this, then the derivative of this. So this really is going to look like something like this. You're going to take the derivative of x squared minus the derivative of xy, and then minus the derivative of y squared. So if you're asking what the derivative of y is, well, it's just y prime, but the derivative of y squared, or let's say y to the third, that's 3y squared, power rule, times y prime. You just tack on a y prime. And so in this case, we had y squared, or we're about to have That's just 2y, y prime. That's the idea. Now, we know we can do the derivative of this, right? That's just 2x. And the problem is the derivative of this and the derivative of this. But this isn't such a problem as much as this guy here, because if we do this, so we'll take the derivative of xy, right? We're going to keep that because this is a little more complicated. Minus the derivative of 2y. Well, we know that we're going to apply the power rule and then tack on a y prime. And then, of course, the derivative of 1, so the derivative of 1, we know this is 0, correct? So it all comes down to being finding the derivative of xy. So what we're going to do is we're going to go off to the side and we're going to actually find what the derivative of x times y is. This is a product rule. This is a product rule. So it's telling you to use the product rule because these are two functions being added or subtracted. Your x is your f of x and your y is your g of x. So we're going to use the product rule here. The product rule states that you want to take the derivative of f of x, which is, in this case, our f of x is x, multiplied by g of x, which is y, and then add that to the derivative, d over dx, of g, right, g prime. So in this case, our g is y, and then we're multiplying by x. So this is 1. So 1 times y is just y, because the derivative of x is 1. The derivative of y is, well, not the derivative of y, but if we multiply 1 by y, we get y, plus y prime x, correct? Because the derivative of y is y prime multiplied by x, it's y prime x. So that's the derivative. So we're going to come back here, we're going to put this back in here. So we're going to say 2x minus y plus x y prime minus 2y y prime equals 0. We're going to distribute that negative, so that's 2x minus y minus x y prime minus 2y y prime equals 0. Now we want the y primes to essentially stay on one side, and we want to get the other terms onto the other side. So we're gonna sort of say that this is minus xy prime minus 2y y prime equals minus 2x plus y, right? Because we're going to bring this, that's plus y, and then this is minus 2x. And then we're just going to factor out a y because we want everything to be in terms of y prime. So y prime is equal to minus x minus 2y equals minus 2x plus y. And then we're going to divide both sides by this. So if we divide both sides by this, we're going to get y prime equals minus 2x plus y divided by minus x minus 2y. And then this is the derivative function. So basically you can think of this, sorry, what did I just have there? I believe I had minus 2y, but you can think of this as being y prime of x. So any value of x you put into this, this function, it will give you the derivative at that point. But you have to specify both the x and the y value. So you have to put so our x was 2, our y was 1. So we're going to put our 1 here, or our x was 2, our y was 1, right? So this is 2 times 2, because our x was 2, plus 1 over minus 2 times 1. That should be 4 plus 1 over negative 4. So you can think of that as 5 over negative 4. So that should be the slope of the tangent line, or not the slope of the tangent line. We haven't plugged it into this formula yet. But just checking our math once again, we did minus 2 times x. So that's minus 2 times 2, which is minus 4. Plus y, which is 1. So minus 4 plus 1 is, so this we want to take a step back here. And I think we sped too far into it, but if we do y prime equals minus 2 times 2 plus 1 over minus 1 minus 2, well, minus, okay, so my x is, let's see, my x is 2, my y is 1, right? So my x goes here, and then in my denominator, I have minus 2, and then minus 2 times 1. Okay, so my y prime is minus 4 plus 1 over minus 4. This should be minus 3 over 4. So, well, not my y prime. This is my m. Remember that once you're plugging it in, you're getting your value of m. So this is your y prime. This here is your m. Okay, your y prime concluded once you did implicit differentiation. But then when you plug your x and your y into it, you're actually getting the value of m. So m is this, right? M is this. M is negative 3 over negative 4, which is just 3 over 4. So this is your m value, correct? This is your m value. So you look back at y minus y1 equals mx minus x1. And the idea is that you plug in your y here, so that's y minus 1 equals 3 over 4, and then we have an x here, correct? So that's just our x, and then minus x1. Well, what is x1? x1 is 2. That's just 2, all right? So y minus 1 equals, you can say that this is 3 over 4x minus 6 over 4. So you can say that this is y minus 1 equals 3 over 4x minus 3 over 2. And you're going to add 1 to both sides. So you're going to say this is y equals 3 over 4x minus 3 over 2 plus 1, which you can think of as 2 over 2. So this is y equals 3 over 4x minus 1 over 2. And that is the slope of the tangent line. So what did we do, right? We were given an implicit differentiation problem. We found y prime. We took our x and y value and we put it into whatever we got for y prime. That was the value of m. And then we took m and we put it into the slope of the tangent line equation, and we got this as an answer. This is the next problem here, and it essentially wants us to find the derivative, I believe, and we want to use a formula that we're now acquainted with, which is that the derivative, d over dx, of 1 over x, or actually the derivative of the natural log of x, or ln of x, is equal to 1 over x. So this is like the formula that we're given, correct? So the idea here is to first do the outer layer, keep the inner the same, multiplied by the derivative of the outer layer. One thing to note, right? I just want to, clarify something here, that that when they say sine of 2x, this is equivalent to sine of x squared. That these two mean the same thing. They just don't want, it's just another way of essentially expressing this. So if I said cosine of 2x, that's the same thing as cosine of x squared. Okay, that's just a brief note to take away. So first we're going to take the derivative of ln of x, right? Now the derivative of ln of x, so we're going to say that f prime of x is the derivative of ln. We're just taking the derivative of ln, and that we know is 1 over x. But so that means that the derivative of ln of a red dot is 1 over a red dot. So if I said the ln of sine of 2x, that should be 1 over sine of 2x, correct? So that means f of x is 1 over sine of 2x, right? But the thing is that we have to go back and take the derivative of the inside function, correct? So we're going to multiply by the derivative, d over dx, of the inside function, which is sine of 2x, correct? Now, the thing here is that you can essentially, the first point to make clear is that ln of anything is 1 over anything. So ln of sine of 2x is 1 over sine of 2x, but then we have to go back and multiply by the derivative of the inside, correct? And the derivative of the inside is sine of 2x, right? Or at least before we take the derivative, I'm just making clear that we're going to multiply by the derivative of the inside. So this doesn't change the fact that this is going to be in our answer. It just says that, this is our answer, but multiply by the derivative of whatever was the inside function, right? Which was sine of 2x. So in this case, the derivative of sine of 2x, you can look at this as, asking what the derivative of sine of x squared is, correct? Because I said that sine of 2x is the same thing as sine of x squared. And you can put the power rule on this now. You can drop this down to 2, and then you have sine of x, exponent is 1 because you decremented by 1, times the derivative of the inside, which is sine of x. So that's 2 sine of x multiplied by the derivative of sine of x, which is cosine of x. So it's 2 sine of x cosine of x. And that's essentially the derivative for sine of x squared. And that's the idea. So you had to use a chain rule on this as well. So it's kind of a chain rule within a chain rule. But your basic takeaway is that this is, you found the derivative of this. So let's put this back here. So it's 1 over sine of 2x. We said that was still in our answer, multiplied by 2 sine of x cosine of x, right? So this is 2 sine of x cosine of x over sine of x squared. You'll notice that 1 sine of x can cancel out with 1, so you could say 2 cosine of x over sine of x. And perhaps you know that this segment here is cotangent, so you could say 2 cotangent x if you really wanted to, but that's your answer. I think any of these would be perfectly fine. So this next problem here is a little more tricky, but I wouldn't say it's not possible to solve. Essentially what it wants you to do is, let me confirm that this is actually the question here, but I believe it is. Right, so essentially what it wants you to do is it wants you to find the derivative of this function, y, but it also wants you to find the second derivative. So all that really means is you're finding the derivative, but you're then taking that answer and you're treating it as another derivative problem. So you're taking the derivative of the derivative, as they call it, the second derivative. So basically, you're looking at two things being multiplied, two functions being multiplied. And this is your f of x, and this is your g of x. So when you're thinking about the product rule, you essentially want to say that, okay, y prime equals, well, I think my marker is a little too thick, but yeah. So what you want to think about is that y prime is essentially the derivative of the first multiplied to the second ln of x, added to the derivative of ln of x, which is our g of x in this case, multiplied to f of x, which is our under root x in this case. So we have it all set up. Now we just have to take the derivatives and multiply them with things. So the derivative of under root x is essentially 1 over 2 under root x. And you can memorize this, but I'll go ahead and prove it off to the side. Under root x can be thought of as x to the 1/2. So you use the power rule here. You have 1/2 x to the negative 1/2. Because I did 1/2 minus 1, which is 1/2 minus 2 over 2, same thing. And I get minus 1 over 2. And then I can bring this into the denominator. I can say this is 1/2 times x to the 1/2. And then I know that x to the 1/2 is equal to under root x. So I can say this is 1 over 2 under root x. You can memorize this like that the derivative of under root x is 1 over 2 under root x, but you don't have to. You could always go back and use whatever we've gathered. But with that aside, I'm actually going to get rid of that stuff because I want to focus on doing the product rule here at hand. So what we're going to do is we are going to continue with the structure that we've carried out for ourselves. And then we're going to multiply by ln of x. Again, we're not taking the derivative of ln of x. We're just multiplying by ln of x because that's what the product rule tells us to do. The derivative of ln of x is 1 over x, then multiplied by under root x, which means this is ln of x over 2 under root x plus under root x over x. We can then do some combining here. So we'll say 2. What we'll say is that this is we have a over b plus c over d is equal to b times d, a times d plus b times c. So we multiply these, multiply these, multiply these. And that is 2x under root x, 2x under root x. And then we have x ln of x on the top plus 2x. Because when you multiply 2x, when you do this, when you do 2 under root x times under root x, you get 2x. Because what happens is if you do under root x times under root x, you just get x. Why is that? Because under root x is x to the 1/2. Under root x is also x to the 1/2. So when you're multiplying exponents, you add the fractions or you add whatever you have. And then once you do that, 1 over 2 plus 1 over 2 is x 2 over 2, which is just x to the 1, which is just x. So that's why I said this is 2x, because when I was multiplying these, I was saying 2 under root x times under root x is just 2x. And that's the idea. That's the basic idea. You can factor out an x from the top. You can say that this is ln of x plus 2 over 2x under root x. Your x's could cancel out. You could say that this is ln of x plus 2 over 2. And then, of course, we had that under root x. So 2 plus ln of x, you could say that this is just 2 plus ln of x, 2 under root x. This here is your first derivative. So this is y prime. Now, what the second derivative says is take whatever you got for the derivative and then take the derivative of that. So what we got for the derivative was 2 plus ln of x, 2 under root x. That's what we got for the derivative. So now we're saying that the second derivative, y prime prime, well, basically we know that y prime is equal to 2 plus ln of x over 2 under root x. So what we're going to do in this case is now we're going to take the derivative of this. So this is asking for the quotient rule. And remember that, the quotient rule says take the derivative f of x, what it says is, take the derivative d over dx of f of x multiplied to g of x, subtract the derivative of g of x multiplied by f of x. And then that's all over g of x squared. That's the quotient rule. So in this particular case, what we want to do is we want to do y prime equals, so the derivative, so we're going to do the derivative, all of this in the top is essentially your f of x. All of this in the bottom is your g of x. So this is your f of x, and then this is your g of x, if that makes sense. So you're essentially doing the derivative d over dx of 2 plus ln of x, and then you're multiplying that by 2 under root x, then you're subtracting that from the derivative, as we said, of g of x. So g of x is what? It's 2 under root x, right? And then we multiply that by f of x. What is f of x? Well, it's 2 plus ln of x. And you could, do 2 under root x squared, or you could say this entire thing multiplied by 1 over 2 under root x squared. Same thing, right? Because if I multiply both of these, I'm going to get all of this over this, correct? So same thing, same thing. I want to focus on the meat of the question, as it were. Derivative, so the derivative of this multiplied to this, that's all we're doing. What is the derivative of 2 plus x? So when you're taking two functions and you're adding them, you can just take the derivative of the individual parts and then add them back together. The derivative of 2 is 0. The derivative of ln of x is just 1 over x. And multiplied by this guy, which is 2 under root x. Subtracted from the derivative of 2 under root x, well, that's just, constant rule, right? So take the 2 out, that's a constant. Multiply that by the derivative of under root x. We said that the derivative of 1 under root x was this. So we're actually going to be doing 2 times the derivative of under root x. And we know what the derivative of under root x is. We said that it was 1 over 2 under root x, if you remember. And then you'd have 2 plus ln of x. And then, of course, all of this would be multiplied 1, 2 under x squared. So hopefully you've been able to follow so far. And what we'll do now is you can clearly see that these 2's essentially cancel out, right? So what you're really left with is 2 under root x, right, over x minus what seems to be like 2 plus ln of x over under root x, 2 plus ln of x over under root x. Multiply that by 2 under root x and then squared. And now, so we're really left with 2 under root x over x minus 2 plus ln of x over under root x multiplied by 1 over 2 under root x squared. Same A, B, C, D pattern. So x times under root x. Multiply this with this. That's 2x, because remember those under root x's, they become x, so that's just 2x. Minus x times 2 plus ln of x. And this becomes 2x minus, and of course we have to maintain the fact that we're doing 1 over 2 under root x squared. 2x minus, so distribute, right? So 2x plus x ln of x, distributing. And then x times under root x multiplied by 1 over 2 under root x squared. So 2x minus 2x minus x ln of x, distributing the negative here. And then x under root x times 1 over 2 under root x squared. These 2x's cancel out. So you're left with minus x ln of x over x times under root x. Okay, so x times under root x, and then times 1 over 2 under root x squared. This is, let's see here. You could cancel out the x's here, right? So you'll just be left with negative ln of x, and then this is 4, so this squared would be 4x, right? Because when you square the 2, it becomes 4. When you square the under root x, it just becomes x. So you're left with minus ln of x, and then we maintained this, right? We had this, and then times the 4 x. So that's just 4x. So you could say your final answer is ln of x, 4x under root x. And that's your answer. That is your second derivative.